Our final speaker for this morning session is Neal Woodbury. He completed his postdoctoral research at the Carnegie Institution of Washington at Stanford before becoming professor of chemistry and biochemistry at ASU, Arizona State University. He served a term as the director of the ASU Photosynthesis Center and also directed ASU's National Science Foundation Integrated Graduate Education and Research Training Program in Biomolecular Nanotechnology and the NSF Research Training Grant. Dr. Woodbury, please. Advance with the green.
Go back with the red.
And you can use that.
Okay, thanks very much, and thank you for the opportunity to speak here. I will be brief, as it is now lunchtime, and talk to you about a rather specific application of a much broader problem that we're working on. The broader problem that we're working on is searching chemically diverse spaces and figuring out ways of searching chemically diverse spaces. And specifically, we're looking at methods in which we can combine ultimately computation and high-throughput synthesis to search chemically diverse spaces. A little bit of that kind of thing was talked about by Dr. Leary yesterday. Our approaches are different in that we're using essentially co-opting the tricks of the trade in DNA chip technology and expanding them to other areas. I probably won't have an opportunity to talk too much about the technical aspects of that today. Instead, I'd like to focus on one specific problem that we're working on and I'm doing in collaboration with Stephen Johnston at the Biodesign Institute and talk about the creation of synthetic antibodies. Now, this work is going on in the Biodesign Institute at Arizona State University, and the thing that we try to do in this institute, which sort of sits on the edge of ASU, and we think of it as a translational group that works with the rest of the university to bring things out into the community. And what we've done is we've picked a series of problems that we want to work on, and we bring together engineers and biologists and chemists and physicists to try to work together to solve these particular problems. And this is one of the particular problems is the one that I'll talk about today. And that problem is the first one on the list here is the rapid pre-symptomatic diagnosis of disease. And the way in which we're approaching that is from the point of view that we really need to be able to analyze a very large number of different analytes in either blood or some other biological fluid. The problem with this is several-fold. One is that, of course, if you want to do something like this, and this is obviously a ways off at this point, you need to make it easy and simple enough so that well people will do it. This is not something that would go in an emergency room. This is something that my colleague, Stephen Johnston, fancifully thinks would be with your Rice Krispies on the breakfast table. Okay, so you would be constantly essentially monitoring the status of your health as a function of time. There are obviously a lot of advantages if you can do this. You actually get a reference to yourself. You watch how your own system changes as a function of time. The other advantage to this is that if you take a very broad approach to it, if you say I'm going to measure thousands of things and I'm going to do that on millions of people on a regular basis, obviously the information and the potential for learning there is tremendous, and you would end up gaining information very rapidly as you utilized this type of instrumentation. Okay, so this is a ways off. We're still trying to simply build the pieces that are required in order to do something like this. And the These are the drivers for it. I think everyone here is very familiar with the kinds of healthcare problems that we currently have, and then there are other issues with regard to emerging threats and ultimately finding and utilizing new drugs, which also could come out of this. But the fundamental problem that you face if you want to do something like this is that you have to start to make very large number of molecular recognition elements. And there are various ways of doing this, but to do thousands of them, to do them quickly, and then to be able to respond as your information content grows and be able to make more and more of these and understand which ones are useful and which ones are not so useful, but create large numbers of these in a way that's economical and simple is a serious issue, and one that we decided to approach in a particular way that I'll go into now. There are problems with using antibodies for this sort of thing, and I think everybody probably immediately sees them. First of all, they're expensive to make. And particularly, it's hard to make large numbers of antibodies. People are doing this slowly, but it's difficult to conceive of making thousands of monoclonal antibodies for this kind of purpose. Surface properties are a significant problem. You make the monoclonal antibodies and you have to put them on surfaces and they still have to work, and et cetera, and that's a difficult problem. And then, as anyone that does much work with antibodies knows, batch-to-batch variation is a significant issue, and one that is difficult to overcome. So there are alternatives to antibodies, and a number of people have come up with alternatives to antibody systems. And I won't go through them all. I'll just say that the one that we have decided to favor is basically a small molecule approach. And the reason for this is essentially that you can make them chemically, you can make them in large amounts, you can make them cheaply. It's just simply a matter of knowing how to create them and getting the geometries and the ligands right. Okay, so this synthetic antibody, SynBody approach is shown here on this diagram. Basically, what you need are 2 or more ligands, and the idea is that you're going to take and find relatively easy to find, relatively weak, relatively non-specific ligands that you can combine together in the right geometry to create high affinity, high specificity antibody-like compounds. All right, and that's been the concept involved here. And so the first question that we faced was, how do we find these low affinity ligands? How do we take those and get them quickly and easily and cheaply from something that we can come up with rapidly? What we decided to do was to start out at least with peptides as a ligand possibility. Obviously, there's been a big history of using peptides for ligands, phage display, mRNA display. There are a number of different methods for coming up with such ligands. We did not want to use those methods simply because they are somewhat slow to apply if you're starting to think about very large numbers of ligands. So instead, we decided to use screening on arrays, and this is where we're doing several different things to do this. We have stock libraries of peptides that we can put on arrays. We currently have a stock library of about 10,000 different peptides that we use for arrays. In addition, we are working on the chemistry and improving the chemistry for doing custom synthesis of arrays of peptides in very much the same way that people do custom synthesis of DNA arrays, which of course allows you to go to very much larger numbers of molecules and screen larger libraries. So the idea is basically you screen on an array for a target. You identify the particular molecules that you're interested in, and I will tell you that knowing which ones you should take off of that array is not a trivial thing, and we can talk a little bit more about that if we have time. But basically, you have to use various methods to first find and then verify that you've got the right kinds of peptides for that purpose. Then you need to optimize the geometry of putting them together. And once you've optimized the geometry, you then do your verification analysis of the particular construct that you've made. There's a couple of different key elements associated with this process. One is that in order to make it work, you need to come up with ligands that bind to different places on the target of interest. You very often, for example, if you look at a phage display library and you take phage display to its limit, you find that you get ligands that tend to go to the same place on most targets, and that would be a problem and the kind of thing that we're trying to do here. So what we've ended up doing is coming up with ways using, in this case, SPR type approaches to tell whether or not we have one or two, whether or not two particular ligands are binding at the same site. So basically you're looking for things that do not displace each other but add to each other in the SPR signal, and one can now do this relatively rapidly after an initial screening of a number of these using array-based technologies. You move then to the SPR platform and then screen for things that bind in separate sites. And this is just an example of having done this for a set of peptides for a particular molecule, transferrin, which is a very common blood molecule, cheap to buy, easy to make measurements on, and figuring out which of the peptides from the original screening will complement each other as good binding agents. Okay, so once you've done that, you've got to optimize the distance. There you have to decide how you're going to put these things together, and that again is a non-trivial issue. It's non-trivial both from the point of view of what kinds of molecules you're going to use and what kind of connections you're going to use, and whether you can get high yields. We started out actually using pieces of DNA for this, and essentially using the kind of DNA technology that was talked about in the last talk, where you can mix DNAs together and get them to fold into the right configuration and put your molecules in the right place. How Yan in our group actually gave rise to one of the slides that was shown in the last talk. And so we worked with him. That works. The problem is that from the point of view of the chemistry involved, the DNA peptide joining has its problems. It's difficult to purify the constructs and whatnot. And so we've decided to go other routes. Primarily, we've been looking at peptide-peptide type linkages, and this has been done using a variety of different chemistries, but there are a number of different fairly well-known and fairly well-characterized ways of linking things together using short peptide strands, which are definable in terms of distances. And so what we've basically done is to create libraries of these linkers, and then you create libraries of your peptides on the libraries of linkers and quickly sort those. And there's a variety of ways that you can do that. The early ways that we've done that just are straightforward ways of doing isolation characterization and then SPR analysis. We're exploring other ways of doing it in a more high throughput fashion now. Okay, so you do this, you start putting these things together. This is a particular synthetic antibody that we've created in this way for AKT1, which is a cancer marker. And what we find, this is just the SPR traces, is that indeed you can come up with molecules this way that have nanomolar binding constants and very long off rates on SPR, which was what we're after. I have to admit, however, right now that this was something of a one-off, and therefore what we're doing at the moment is to go back, work through the entire process again, and make the whole thing robust enough so that we can crank these things out one after another instead of Herculean effort to get one out of the system with a lot of analysis. So that's the basic concept of putting these things together. Beyond that, we are looking very much at ways in which to improve these further, and the ways in which we improve them further are the same ways in which antibodies are improved further in your system, and that is that you do mutational variation of the antibodies after the fact, and that again comes back to this whole business of being able to make custom arrays of peptides and complex systems on surfaces, and then scanning those for mutational analysis. We initially have done our mutational analysis by brute force using mRNA display, just to show that in fact that can work. And indeed, if you select then for the peptides in your construct to be, let's say, a factor of 10 better in terms of specificity or affinity, that translates into a factor of 10 improvement in specificity or affinity in the final construct as well. So all the pieces have been put together at this point, and once we have managed to go through the whole process and get something out that had the sort of characteristics we want, our big emphasis at the moment now is in putting all the ducks in a row in a way that can be done high throughput in a simple and rapid approach. I will take just a couple more minutes to give you a little bit broader view of what we're trying to do. This is just shows the data as you walk through this, starting with some individual peptides and working your way down through the different steps, joining things together. You can get things on the order of tens of nanomolar, and then after doing the mutational analysis, you can get down to sort of one nanomolar. These are all the people that were involved in this work and are involved in this work. I'll take just a minute to, since I'm only at about 15 minutes, I'll take just a couple of minutes to talk about this slide, which tells you about other things that we're trying to do in this area. Because if you start to think about searching chemical space, and particularly if you start to think about what you can do if you can make moderate to large chemical spaces on surfaces and search them, there's really, I think, a tremendous variety of possibilities out there. There's no particular reason why the kinds of technologies that are used in the DNA chip industry can't be applied to a whole range of different chemical constructs, not only linear constructs, branch constructs, etc. And we've been working for the last several years mostly on amide systems and basically nitrogen amines. But there's no reason you couldn't do mixed things between amines and hydroxyls and other kinds of systems as well to make more complex molecules millions at a time. Now, the DNA chip industry, Nimblegen is currently selling chips that approach about 1 million different DNA molecules on a surface. If you start to work through combinatorial ideas about how you could make mixtures of molecules at each spot that would be related to each other, you can start to think about approaching libraries that are similar to phase display on the order of 10 to the 9th, but do so from stock slides very rapidly. And so and of course the other beauty of this is that you get to pick exactly what molecules you make on the surface. At least if you can get your chemistry right, you get to pick that. And those molecules don't have to be biological molecules. You do not have to look at them under biological circumstances. If you'd rather look at them in heptane, that's fine. And you have the opportunity to select them you have the opportunity to actually look at the activity of all of them on the surface. And while that may sound trivial, it turns out that's extremely powerful, to know what each of them does and doesn't do, and be able to use that in formulating the next generation is very useful, rather than just simply being able to say, I found the ones that bound, or I found the ones that had a particular catalytic activity, and that's all I get. I don't get to find out which ones didn't work. Knowing what didn't work, or what worked halfway, or what worked a little differently is an extremely powerful tool from a chemist's point of view in then being able to make conclusions and decide what the next library really should look like in going forward. So that's the bigger picture, and we're doing a lot of things with that, from catalysts, mostly in the energy world, to synthetic ligands, to things for mapping antibody sites and these sorts of things. So a lot of possibilities there. I will stop so that we can get to lunch. Thank you very much.